All right, welcome to episode 13. So we've got a few things to do in this episode. We're going to put a ZIF socket on our passive backplane. That'll make it easy to insert and remove the ROM chip as we work on firmware. Then we'll add some peripheral devices, specifically an 82C55A peripheral interface chip that gives us 24 digital I/O pins. An 82C54 timer counter chip, and we'll use that to generate the transmit and receive clock for our UART. Eventually, we'll also use it to generate a timer interrupt signal. And then we'll add an ACIA device that is a UART chip for serial communications, and that'll allow us to actually do serial communications between our host PC and the target 6809 system. And so, as always, the schematics and code for everything we discussed are on the GitHub site, and look down in the video description for that link. Okay, let's get started. All right, so here's some important progress. I'm working on this second module of the 6809 system. The core module is back here. It's kind of hard to see, but it is working. This module is going to contain the ROM and the RAM and some peripherals. Right now, I just have it populated with the ROM and the RAM. And basically, it is working. I have the count program from the previous two episodes running. It basically just repeatedly increments a variable in memory and sends the value to an output port, which you can see on this hex display. And so all of this is working, and what is kind of significant is that it shows what prototyping is going to look like in the future, in that most of the circuitry is here on these modules, and then I just take signals off of the backplane as necessary to prototype whatever I'm working on. So right now, as you can see, the only signals going on to this breadboard where the output port is the data lines and the memory write signal and a chip select, and those are the only wires that need to go onto this breadboard. So in the future, it should be a considerably more pleasant experience to prototype and develop firmware for new devices. One thing you'll notice here is that I've started to add a ZIF socket to the prototyping area of the backplane, and that's actually where the ROM is going to live. It would be very difficult and probably wouldn't work to repeatedly pop this EEPROM out every time I want to update the firmware. So instead, that's actually going to live in this ZIF socket, basically for development purposes. But in any case, this is pretty cool. We've got basically almost the entire circuit running on modules off of the backplane. Okay, so I finished soldering the ZIF socket onto the prototyping area of the backplane here. I just did point-to-point connections of the EEPROM pins on the ZIF socket to the appropriate backplane signals. If you've ever watched any of Ben Heck's videos where he does hand soldering onto a proto board, basically he cuts up a ribbon cable for the individual connections, and that's what I did here. It works out quite nicely because they're nice and thin and flexible. You just expose a little bit of wire at the end and then solder that to your pin or your pad or wherever you want to make a connection to. So basically I'm going to now continuity test everything to make sure I've got everything connected up properly, and we'll see if I can run the system with the ROM in the ZIF socket. Okay, so looks like the ZIF socket is operational. Here's the ROM in the ZIF socket running the count program, and it does seem to be working as it was earlier. I've taken the EEPROM out of the socket on this module. The static RAM is going to stay there. But yeah, things seem to work, and this is pretty exciting for me because at this point I should not need to take the core module out again. I shouldn't need to sort of disassemble the backplane. Everything is pretty much ready to go, and future prototyping will more or less look like this, where I have breadboard set up for whatever specific device I'm working on interfacing, and I'll just bring use jumper wires to bring signals off of the backplane as necessary for whatever I'm prototyping. Okay, so the next thing I am planning to do is to integrate the 82C55A peripheral interface adapter. It's basically a GPIO device that's going to give us 24 GPIO pins. Okay, so I'm going to get that started. All right, so before we move on to the 82C55A, let me point out that we've reached an important milestone. So this, on these breadboards, is the prototype circuit I've been working on since episode 8. I'm about to take it apart. I don't need it anymore. Basically, everything we have here exists now on these modules and the backplane. And as you can see from the wires here, this has gotten quite hard to work with. This is going to be a lot easier to work with. So, this prototype definitely served its purpose, but it will be satisfying to take it apart because I guess the future has arrived. All right, so here's some initial success with this 82C55A chip here. I have it basically running a modified version of the count demo program. So the CPU is, counting up using a variable and outputting the value of the counter basically by writing it to port A of this 82C55A. Basically everything was fairly straightforward. I made some dumb mistakes. I had the initially I had the ground connection on the wrong pin. I forgot to hook up the address lines. It has two address lines, as we'll see in a moment when we look at the schematic. I forgot to set the initial stack pointer because the program uses subroutines, and that is not going to work at all unless the stack pointer is set in a valid area of RAM. So this is good progress. So let's look at the schematic. All right, so here's the schematic. I've added a new section of the schematic for peripheral devices, and right now the only thing that's in here is the 82C55A, and it's very easy to interface. You hook up the data lines to the data bus. It has two address lines because there are a total of 4 registers that are sort of internal to the device to allow you to control it. It needs a chip select, it needs memory read and write signals, and it takes an active high reset, which our MAX 708 chip does generate. And basically what it gives you is 24 pins of digital I/O, organized as 3 ports: port A, port B, port C, and there are all kinds of fancy modes that you can run these ports in, but the most common one, and the one that we'll be using, basically you just designate particular ports as either input or output, and then if it's an output, you write a byte of data to it, and the bit pattern in the data byte appears on the output port. If it's configured for input, then the logic levels of the signals connected to these pins can be read by doing a memory read from the corresponding register. So it's relatively easy to use. All right, so let's take a quick look at the code for controlling the 82C55A. So this assembly file just has some definitions associated with programming the device. It shows defines the offsets of the registers relative to the base address where the device is mapped, and there's 3 registers that are basically the data registers for the A, B, and C ports for input and output. And then also the 4th register is a control register that allows you to configure modes and data directions and things like that. And then the rest of the definitions are basically just bits that can be set in the control word that is written to the control register to configure the device. We're just going to set it up in the most basic mode, which is mode 0 for every port, and we'll just set every port to outputs for now. Let's see, so let's look at the ports include file, and I will be updating this as new devices are added, but basically for each device that is, each peripheral device that is in the system, we want to set up the base address and then have additional definitions for the various registers of that device. So I've done that for our 82C55A. Okay, and then finally, let's look at the count test program. Here's the count test program. So we include those 2 header files, kind of do our usual preamble stuff to set the origin address for the code to hex 9000, because that's where the code starts. And then this is basically the same as the count program we had a couple episodes ago when we tested the RAM for the first time. Basically the main difference here is that we are calling this I82C55A init subroutine to initialize the device, and basically all it does is constructs this very complicated, uses this very complicated instruction or expression to compute an initial control word value that we'll write to the control port. This is actually just a really, really fancy way of writing 0, because basically if you set all bits to 0 in the control word, you effectively get all of the ports in mode 0 for output, which is what we want, and then we simply write that control word to the control port, and that configures the device. And at that point, it's basically set up as a memory mapped I/O device, and basically whenever we output a byte value to this address, or the memory location at this address port, I82C55A underscore A, that's the address of the register associated with port A. Basically that data gets sent to the device, and because that port is configured for output, basically whatever bits we write will appear on that output. And so that's exactly how we were generating the data values that were sent, that appeared on that little hex display when we showed the actual circuit in operation. So basically this is nice. We now have 24 pins of GPIO. All right, so just for the sake of completeness, here is the 82C55A datasheet. This is the Intel one. Other manufacturers also made compatible devices, and they're all kind of the same for our purposes. And essentially all I wanted to show here was to just note the pins associated with the output ports, or I/O ports. So here's port A, PA0 through PA7. Port B is over here, PB0 through PB7. Port C is split into two parts, so PC0, PC3, PC4 through PC7. So 24 of the pins on this device are just I/O pins, and you connect them to whatever you want to either control or sense in your application. And if you read the actual datasheet, there's all kinds of fancy modes and things that the 82C55A can do, associated with things like interrupts and sort of bus type stuff. We're just going to use it in the most straightforward way, just purely as output or input. Right, so just for fun, I took out the 82C55A and put in an 8255. This was the non-CMOS original version, and I pulled out the most ancient one that I could find, which is this ceramic one that I think is a National Semiconductor or something like that. Works perfectly fine. So that was kind of fun to see that these really old parts, can still function. Anyway, thought that was fun. All right, so here's the actual 8255, this old ceramic one. Here's also another one I have that's an AMD one. Both of these are from 1981. I don't know, for whatever reason, I just get a kick out of using these really old chips. It's kind of a connection to the past. All right, so here is the 82C54 wired into the circuit. It was pretty straightforward interface. I just hooked up the 8 data bus lines, the 2 low address lines, A0 and A1, the memory read and memory write signals, and then 1 chip select signal. That's all we needed to interface this. And essentially, what I want to see here is I have configured timer counter 0 to take the processor's E signal and divide it by 6 and output a frequency that is 1/6 that of the E signal. So let me now explain my rationale for doing that. All right, so what we're doing is the processor's E signal is the frequency of the crystal oscillator, which for my circuit is 3.6864 megahertz. The E signal basically divides that frequency by 4, which is 921.6 kilohertz. And the E signal is essentially used for the bus timings for memory reads and writes, but we are kind of repurposing the E signal to generate an appropriate UART frequency for serial communications. And the way this works is that we take the E frequency, 921.6 kilohertz, divide it by 6. We've got the timer counter 0 set up to divide its input by 6. That's going to produce a frequency of 153.6 kilohertz. If we further divide that 153.6 153.6 kilohertz by 16, that produces a baud rate of 9600, which is exactly one of the standard UART frequencies. And essentially, when we hook up our UART, we will enable its divide by 16 mode in order to take its clock input and produce the appropriate transmit and receive frequency. So essentially, the purpose of timer counter 0 is to generate our UART frequency. Well, I almost forgot the most important part of showing this circuit, which is to actually test the frequency that's being output by timer counter 0. So here we go. Yeah, 153.6 kilohertz. So that's exactly what it should be. So that's good. All right, so very briefly, let's look to see at the updated schematic with the 82C54 in it, and I've sort of fed in correct appropriate signals that are necessary for the 82C54, including the chip select, which is the second chip enable that we generate for kind of internal I/O devices, and not a whole lot to say here. I mean, the data bus signals feed in, memory read, memory write, address signals, chip select. The one thing that is maybe a little bit useful to note is that the E signal from the CPU is being fed into the clock input for each of the timer counter units, and I don't show anything happening with the outputs yet. We'll get there. These G inputs, they are gate inputs that are basically used for event counting if you're using these as counters, which of course we're not, so they're all just tied high. All right, so that brings us to the third device we're going to interface, which is the ACIA, Asynchronous Communication Interface Adapter, and there are different versions of this chip. So this one here is the Motorola 6850. That's the classic one. This is the Hitachi 6350. Specifically, this is the B speed grade, so 63B50. I'm going to use this one, the Hitachi one, since it's CMOS, requires a little less power, also can operate at higher bus speeds. So let's get that integrated. Okay, so I integrated the ACIA UART chip into the circuit, and pretty straightforward. Once again, you just need your data bus connections and appropriate control signals. One thing I noticed that I had forgotten about is that because this is a Motorola chip, it doesn't take memory read and write signals the way that nearly every other 8-bit peripheral does, like all of the Intel chips. It actually expects to get the E and read-write signals from the CPU. These were basically the signals that Motorola designed, to synchronize, memory bus transactions between the CPU and all of their peripherals. And what I neglected to do is put the read-write signal on the backplane. So I need to fix that. The good news is, if we go over here to the core module schematic, I do have this 74HCT365 hex buffer chip. And I actually did have an unused input on this. This last input was originally just tied to ground. So I'm going to put the read-write signal from the CPU there, and then it can be sent out onto the backplane along with the other control signals. But I will need to do a little bit of soldering on the core module. So I'll do that and meet you back. Okay, so I have now the read-write signal on the core module here going from the CPU to the hex buffer onto the backplane, and then on the breadboard here I have my 63B50 ACIA chip all wired in. One mistake I noticed on the schematic that I found with a little bit of trial and error today is that I forgot to feed the low address line into the ACIA, because there are some internal registers that you select between using the low address line. So got all the connections done here, and I have the transmit, receive, and handshaking signals going between the ACIA chip and this FT232RL USB to serial adapter, which in theory should allow me to run a terminal program on my PC to communicate with the 6809 system. So let's look at a little test program and then see if it works. All right, so here's the code for the ACIA, and you know the drill here. We have a header file that has various definitions pertaining to bits of the control register and the status register, so we can understand what the device is doing and control it. For example, things like data formats, what clock divider to use for the input clock. For transmit and receive, various sort of like interrupt modes and things like that, and then constants associated with data transmission. So let's see, I refactored the code a little bit so that now all of the device-specific include files are included by this single include called io.dev.asm, which then also defines the addresses for hardware registers. And so essentially programs just need to include this one sort of consolidated header file. So I have the ACIA device mapped at hex 8040, so that is the third of the chip selects that are generated for kind of the beginning of the I/O address space. So here is the test program, and the main thing that we need to do is determine the clock divider. We saw that when we set up the 82C54. So essentially this is the amount by which the E signal is divided in order to get the clock that is output by unit 0 of the 82C54. That goes into the ACIA, which further divides it by 16, and that produces our 9600 bits per second data transmission rate for transmit and receive. And we have other sort of parameters, like, for example, the data format being set here. And there is a subroutine, ACIA init, that is responsible for basically setting things up. And one of the cool things about the ACIA is that it is, kind of ridiculously simple to send and receive data. Essentially, you just do so for example, here's the ACIA send routine, and essentially all it does is a tight loop that continually checks the status register until it finds that the 1 byte data transmission buffer is not full, and as soon as that's the case, all you have to do is write your data byte to the send register, and that's it. And then receiving is similarly quite simple. You just have a loop that continues as long as the receive buffer is empty. As soon as it's non-empty, you read the data byte from the receive register. So it's pretty simple to use. I wrote a little subroutine called ACIA send string, which allows you to send a null terminated string of bytes. Basically sends everything up to but not including the null terminator byte, and I have this little test message here to test to see if that's working and to see if we can send some data. And so essentially this is the same as the count program. However, it does send that one string when you start the system up. Okay, so here's my little terminal program. So I am resetting. I'm going to reset the core module here to reset the system, and essentially I have the terminal program connected to dev TTY USB 0. That's the USB to UART adapter. So I'm hitting reset, and there's our message. I realize the font's a little small, but that is data that was sent by the 6809 system and was received by the terminal program on the host PC. So we now have communications established between the PC and the target system, and eventually what we're going to do is develop an interactive monitor program to allow us to basically control the 6809 system and test things and eventually load programs and do stuff like that. All right, so before we wrap up, let's take one last look at the schematic for the peripheral devices, and in particular, how we've integrated the ACIA device. And a couple things that have been added here. Here's address line 0 that feeds into the RS input on the 6850 ACIA device. I think that means register select. It allows us to select between hardware registers on the device. And I've also shown the connections to the FT232RL USB UART converter, and essentially through 4 2.7K resistors, the receive data, transmit data, RTS and CTS signals from the ACIA device are connected to corresponding signals on the USB to UART chip, and basically just sort of make the connections to these exact signals on the breakout board, and that should allow the ACIA to communicate with your host PC through the USB adapter. All right, so let's talk about what we'll do next. So currently, these peripheral devices, the 82C55A and so forth, are just on a breadboard, and that's great because we proved that the circuit works. The next step is to actually put them onto the PCB for the second module. That's the one that contains the ROM and the RAM. Those peripheral chips will also live on that module. That'll make it a permanent part of the system. Now that we have serial communications working, this would be a good point to start working on a ROM monitor, so we can basically interact with the 6809 system using a terminal program. And then as far as sort of hardware development, probably the next step will be interrupt handling, including support for a timer interrupt generated by the 82C54. Okay, so I will see you in the next video.